Welcome back to Destinies Today. Let's embark on a breathtaking journey through the cosmos, exploring the fabric of space and time. Picture this. We're in the vastness of intergalactic space, billions of kilometers from Earth, floating between our Milky Way and the Andromeda galaxy. Both galaxies shimmer with countless stars, yet around us, space feels eerily empty. But we're not lost in nothingness. A cosmic web surrounds us, the very framework of the universe, SpaceTime. This invisible grid, woven from countless tiny particles, reveals the universe's hidden geometry and dynamics. Here, the grid is still, undisturbed. Toss a marble, and it glides straight through the void, forever. But SpaceTime isn't truly static. Zoom forward in time, and it drifts gently, like a river carrying stars, gas clouds, and dark matter. These massive objects warp space-time, tugging the universe's fabric toward them. Slowly, the Milky Way and Andromeda draw closer, destined to merge billions of years from now, long after we're gone. Rewind to the early 20th century, when researchers discovered something astonishing. Most galaxies are drifting apart. The universe is expanding, its grid stretching like elastic, carrying galaxies farther from each other. As it expands, the light from these galaxies stretches, shifting red, a phenomenon driven by the mysterious force of dark energy accelerating the universe's growth. This expansion traces back 13.8 billion years to the Big Bang, when the universe, once a dense soup of fluctuating energy, exploded into existence, ballooning to cosmic scales in a fraction of a second. What came before? That remains a mystery. From those early fluctuations, matter began to clump, forming vast filaments, halos, and eventually galaxies, stars, and planets like Earth. Our home orbits the Sun, a star that warps space-time with its immense mass, pulling the cosmic fabric inward. Planets, asteroids, and comets follow this curve, orbiting the Sun without drifting away. They move straight, but the warped grid keeps them tethered. Earth, too, bends space-time, holding the Moon and our satellites like the International Space Station in its grasp. Far from Earth, the grid flows gently, allowing fast-moving objects to escape. But closer to the surface, the grid tightens, accelerating. Rockets must reach incredible speeds to break free from Earth's pull. Drop an apple, and space-time guides it toward Earth's center. Release several apples, and tidal forces, caused by the grid's flow, pull them together in one direction while stretching them apart in another. This is the dance of the cosmos, where gravity and space-time choreograph the universe's every move. The Moon's gravitational pull tugs at Earth's oceans, creating the rhythmic dance of tides. This back-and-forth motion stems from Earth's 24-hour rotation, which drags the space-time grid ever so slightly along with it. When an apple falls, Earth's spin subtly bends its path, even without contact. Deep within our planet, the space-time grid continues its descent, drawn toward the core. Yet Earth's materials resist collapse, exerting immense outward pressure. This force grounds us, felt in our legs when we land after a jump. At the planet's core, the grid converges, and a marble, were it able to withstand the crushing pressure, would sit motionless, suspended at the center. Particles in the grid press forward, rebound, and emerge on the other side. If we could leap through Earth, we'd pop out on the opposite end. In 5 billion years, our Sun will face its end. Unable to sustain its internal pressure, its core will collapse into a dense white dwarf, while its outer layers balloon into a vast planetary nebula. But not all stars fade so quietly. A supergiant star, 20 times the Sun's mass, burns its final fuel hundreds of light years away. Its core buckles, and its outer layers erupt in a supernova. The core compresses into a neutron star, packing the mass of 2 suns into a mere 30-kilometer sphere. This extreme density warps space-time so intensely that even light bends, creating eerie optical distortions. Further away, an even more massive star meets its fate. Its core collapses in an instant, and its outer layers explode outward. The universe's pull overwhelms the core, condensing it into a tiny sphere where space-time curves so drastically that nothing, not even light, can escape. This is a black hole, a cosmic abyss where the grid flows faster than light, trapping everything in its relentless current. Some black holes form near companion stars, drawing in glowing plasma that spirals into an accretion disk. This disk, orbiting the black hole, loses energy and inches toward the event horizon, where matter is torn apart, stretched into thin strands, spaghettified as the grid accelerates infinitely near the core. Our understanding of quantum physics falters here, unable to fully describe this extreme environment. Black holes often spin, a legacy of their parent star's rotation. As a star's core collapses, its spin accelerates, like a figure skater pulling in their arms. This rotation twists the space-time grid, creating a vortex within the black hole's ergosphere, a region where everything, even light, is forced to rotate with it. Beyond the event horizon, where the grid falls faster than light, a rotating black hole may harbor a theoretical inner horizon, where centrifugal forces slow the grid's plunge. Some models suggest white holes, gateways to parallel universes, but these inner horizons are likely unstable and may not exist. The true nature of a black hole's core remains shrouded in mystery. When two black holes meet, they spiral in a cosmic dance, accelerating until they merge into a larger black hole. This new entity vibrates like a struck bell, sending ripples through the universe, gravitational waves. These waves, more powerful than the light of all stars combined, travel at light speed, warping everything in their path. On September 14th, 2015, such a wave, born from a cataclysmic merger over 1 billion years ago, brushed Earth, shifting it by a fraction of an atom's width. Detectors caught this fleeting tremor, marking the dawn of gravitational wave astronomy. This new field lets us probe the universe's very fabric, revealing secrets of its most violent events.